Hello everyone, welcome to this session on Amazon SageMaker Fridays. In today's session, we're gonna discuss about how to build high performance, energy efficient, and cost efficient applications using Amazon SageMaker, supported by AWS Trainium and Inferentia instances. My name is Arun Kumar Lokanatha. I'm a machine learning solutions architect, part of SageMaker team. I'm joined by two of my colleagues, Raghu and Casey.
Hey everyone, this is Raghu Ramesha. I'm a senior machine learning architect in the SageMaker service team. I help customers build, deploy models on SageMaker.
Hi everyone, my name is Casey Tung. I'm a senior solution architect in the Annapurna lab, and our organization builds custom silicon chips such as Trainium and Inferentia. And my role is to help customer get onboarded with their model, regardless of their platform of choice, using Trainium or Inferentia. Glad to be here.
Cool. Let's get started. So AI has been around for a very long time, but when we see it's over the last decade or so, we have seen a flywheel, a virtuous cycle in evolving evolution of AI/ML. So first, it starts with innovation of a new model, innovating ways to speed them up, which typically unlocks a variety of use cases, variety of applications, and then companies, when they build these applications, they want to embed them into their products to delight their customers, which increases the demand and which in turn drives the need for additional investment to make a better infrastructure, better tooling, and better softwares. This of course, internally fuels the innovation, and this cycle continues, giving us scope for evolving the AML landscape. So let's review the latest trends in AI that are propelling the flywheel we looked in the previous slide. So customers are driving AI innovation at an accelerated pace to keep up with the applications use cases which meets their demand. So possibly the hottest topic in today's deep learning paradigm is large language models or the large models in general, which are basically driven by transformer based architectures. So in recent years, we have seen these models have gained popularity due to their state-of-the-art accuracy and scaling properties. More customers are adopting these language models for their use cases. And these models have scaled all the way from millions to billions to trillion parameters. With we have seen some customers or companies building trillion scale parameter models as well. Another critical enabler is the advent of self-supervised learning, which helps data scientists tap into the vast wealth of unstructured and unlabeled knowledge available online. In turn, this helps in boosting model accuracy and supporting training these large language models with billions and trillions of parameters. The last element, but really critical for innovation, is all these state of the art models, such as the diffusions, Falcon, Llama, and many of those are open source contributions. This contributions helps increase adoptions for newer architectures and helping customers to kind of adopt them to their use cases to improve efficiencies. So let's take a look at where customers are using these models for their use cases. Uh, Large models, they generally found usage in uh, applications such as code generation, where you use a large model to generate code recommendations or even do code reviews. The second use case, which is more popular, is image generation. You would have seen models like diffusion, which can be used to kind of generate high quality images with a short snippet of text description. Um, we also see applications of large models in music generation, video generation. There's some of the models that generates videos based on a description. When it comes to large language models, we have seen a multitude of applications where customers are seeing success, starting with text generation applications for productivity. Like say, if you want to create a description for a product or any onboarding documents, customers were able to use LLMs to generate text. Uh, Another use case is like chat or virtual assistant, conversational interfaces where LLMs can be used with a context to answer questions pertaining to the customers. And finally, we also see adoptions in text summarizations where large language models are used for summarizing a long document, right? So with good quality outputs, which are pretty much similar to what a human generates. And finally, there is a good application in search where LLMs are used to generate embeddings for documents which are indexed in databases or open search and retrieved based on the user query. So there's a huge set of applications that are being driven by the large language models. And why is this happening, right? So there is a bunch of models that's been built and open sourced in the last few years. We had BERT like few years back, which was million parameter models, and GPT came. Then there is Llama, there is Bloom, we had Falcon. So all these models are evolving at a very fast pace, and each of these models, when they are out, they kind of achieve state of the art accuracy in all the open tasks that's available, and that way customers are also able to take this and easily adapt them or fine tune them to their use cases. And most of cases, they can directly deploy these large models and then get uh, immediate results what they need. So let's take a look at some of the common challenges and trade-offs. So first and foremost is developers are trading performance and cost. So if you want to train these large models quickly, you need to deploy them to a cluster of GPUs. This is expensive. This is one of the main reasons uh, building LLMs are only for done by a handful of people, but more customers they want to generally adopt them and then use them for downstream tasks. The next thing developers are considering is how to use these models at a low cost. So these models also two things, right? One is how do they reduce their cost, at the same time how do they achieve the required performance like latency or throughput needs, etc. The third challenge is how easy it's to use this large models, and how they can take this, either fine tune them or deploy them based on their specific use cases. Lastly, sustainability. It's another important factor. The bigger the model, the more impact it has on the environment. So, how can we make sure we use the models which are right size for our use case, and so that we are also kind of considering its impact on the environment. So to with the above mentioned challenges considered into account, we have been investing in coming up with most price performant, energy efficient, uh, scalable architectures or scalable hardware that can be used to build these large models, either tune them or deploy them using AWS built hardware. As you can see, so we provide three options. One is AWS Inferentia, which gives you low cost per inference in the cloud. Inferentia comes with two flavors. We're going to be discussing this in more detail later on in this webinar. Inf1 and Inferentia 2. And we also have a custom chipset for training, which is AWS Trainium. All these chipsets, they give you very good price per performance, all the way from 40% to 70% lower cost, also giving you a very good performance either in terms of latency during inferencing or in terms of training, throughput during training. So let's get started by looking at training first. We will take a look at SageMaker, SageMaker is a fully managed service that gives you multiple features or services for building, training, and deploying and monitoring your machine learning model. SageMaker kind of gives ready-to-use features across your ML lifecycle. And let's start by looking at how do we train these models, right? So how do we train models using SageMaker training by using Trainium instances? So when you look at large scale training or a large model training, there are three different aspects that we generally look at. The first is the compute. SageMaker provides compute with many options to choose from, all the way from GPUs to AWS Trainium, which is available as part of SageMaker. We're going to focus on Trainium today in today's session. Uh, Apart from compute, uh, we also need look at the platform features, right? So that helps in either fine tuning or training, even training a foundation model with SageMaker. So in terms of platform capabilities, SageMaker allows us to do large scale orchestration where you can easily spin up a cluster with multiple nodes, and SageMaker make sure it scales up and gives provides a cluster, and it shuts down once your training is done. We also make sure we do health checks on all the instances that we provide before you launch a training on SageMaker. So these health checks we do for GPU based instances. And as part of SageMaker, we provide something called as Jumpstart, where you can readily take any foundation model and you can deploy them or fine tune them depending on use case. Also, to help large model training and fine tuning, we provide features like SSH integrated training container, memory profiling, debugging, and also options to load your data, right? So we might deal with large data when we deal with large models. So we provide options to kind of stream your data from S3 or load data from a shared file system like an FSX onto your training cluster. Lastly, once we have the platform in place, then you need to have training libraries, distributed training libraries and frameworks. On SageMaker, we support TensorFlow, PyTorch as one of the main supported frameworks. And we also have our own distributed training libraries, and you can also bring your own libraries. We also support Neuron distributed, which can be used for training large models on Trainium. So with that, let's quickly look at what Trainium is and what benefits we get from Trainium, and before we dive deep into running a training on SageMaker using Trainium. So the Trainium powered TRN1 instance, it gives you 1.4x the performance at half the cost when compared to a similar instances on AWS. So Trainium comes with two configurations. One is TRN1 2x large, which has got one Trainium chips with two neurons part of a single chip, and there is a TRN1 32x large, which comes with 16 Trainium chips, which is 32 neuron accelerators. And each neuron accelerator comes with 16 GB of GPU, so thereby making it 512 GB for a TRN1 32x large and 32 GB of instance memory in case of TRN1 2x large. So the network here is networking is based on second generation EFA, EFA v2, which enables low latency and improved cluster level scaling. So let's take a look at some of the supported models on TRN1. Today, so we support quite a lot of large language model architectures, starting from GPT-based models like GPT-2, GPT-NeoX, and we also support Llama 2, You can train Llama models 7B and 13B at this point in time. And we also support support for Falcon and Bloom are coming soon in the near future. So when we talk in terms of performance, we when we have benchmarked Trainium against similar comparable accelerators on AWS, where when we take a look at the BERT model training, uh, we have we benchmarked all the way from one node to using 16 nodes on a cluster. Trainium in terms of throughput as well as training cost. When it comes to throughput, Trinium gives you 1.5x more performance on a 16 node scale. Even on a single node scale, you get a 1.2x faster performance, right? And when it comes to cost, Trinium is 2.3 times cheaper when you are looking at a 16 node cluster scale. And even at a single node, it's about 1.8x lower cost when compared to a similar accelerator on AWS. When it comes to LLM training, right? So we have benchmarked against GPT-3 GPT architecture with three different model configurations. One is 24 billion parameter, 46 billion parameter, and 175 billion parameter. On 24B parameter, we see a 43% higher throughput when we trained it using TRN132X large. Similarly, we see a higher throughput when we use it on a 46B parameter model and 31% higher throughput when we train a 175 billion parameter model. So with that background, let's take a quick look on Trainium architecture itself. Uh, Trainium, so each Trainium chip, like we saw TRN1 2x large has got one Trainium chip, and then TRN1 32x large as 16 Trainium chips, right? So each Trainium chips has got two neuron cores. It comes with two neuron cores, and each of them has 16 GB of HBM memory. And it also comes with a separate engine for tensor engine, which is used for larger matrix operations such as your math multiplication or convolutions. There is also a separate scalar engine, which can be used for element-wise operations such as your activations. And we also have a vector engine for aggregated operations such as like pooling, vectorization, etc. And it comes also with a GPS IMD engine, which can be used for custom operations. If you want to write your own custom operations, we support that as well. Since we have a separate engine for each types of processing, it makes Neuron much more efficient uh, compared to other accelerators out there. And in for inter neuron core communications within an instance, we have a neuron link V2, which enables fast communications between each neuron cores. So with that architecture, we also have certain other features that are optimized for ever evolving large models out there. So we have novel data type support apart from the basic regular FP16, BF16, FP32 kind of a support. We also support CFP8 data types as well, and much more. And the second thing we have is an hardware accelerator stochastic rounding. So this is a probabilistic rounding mechanism that works at an hardware level, and this helps in improving the performance when you are training a model at large scale, right? And lastly, we also provide abilities to write your custom operators. We have a C++ wrapper mechanism through which you can write your own custom operators for Neuron. and what it takes for training on AWS, right? AWS training. Uh, we support like mixed precision format that you used with PyTorch, something like Torch Autocast, which you can leverage to kind of train a model on Trainium. And for models itself, we support two types of parallelism. One is the distributed data parallel. This is useful when your model fits in a single neuron core. And for data parallelism, we support task.distributed. And we have our own collective communications for all reduce, all gather, and reduce scatter that works with task distributed. Similarly, when dealing with large models, we need a model sharding mechanism or a model parallelism mechanism. We have support for like we have a neuron optimized neuron Nemo Megatron, and we also have a neuron distributed package, which can be used to train large models like a GPT Neo X or a Llama 2 and so on. All right. So with that background on Trainium, let's take a look at what it takes to use a Trainium instances with SageMaker training. For running jobs on SageMaker training, we provide a Python SDK, which can be installed as a pip package and which gives you easy mechanisms to submit a job onto a SageMaker training cluster. So the SDK is much simpler to use. You start by selecting which estimator you want. We support PyTorch, TensorFlow. We also have an Hugging Face estimator if you are working with Hugging Face models. And the PyTorch estimator can also be leveraged for training Hugging Face models as well. Few things that we provide to this estimator. One is the entry point where you specify your training code and then you specify what instance type we need. We can choose between TRN1, 2x large, and 32x large. We can also run a distributed training by providing the instance count. Then we choose the framework version. This is the PyTorch version. We are choosing 1.13 and Python version to be 3.10. And once we specify that to run a distributed training, SageMaker estimator integrates directly with TorchRun. So we enable that by providing the distributed mechanism for Torch distributed enabled as true. So what this internally does is like it uses TorchRun to launch a distributed training cluster and run the code that we specify on each of the neuron cores. Finally, we pass the data to the estimator. The data sits in S3. We pass it as a data channel, which SageMaker uses for training. So behind the scenes, when we submit the estimator.fit, SageMaker is going to launch a cluster with Trainium instance. It's going to copy the training code from S3 training code into that instance, and it's going to copy the data from S3 into the training instance. It also copies the neuron containers that we provide that can be used on Trainium instances into the instance. It runs the training, and the training generally involves two phases when we use Trainium. The first thing is we compile the model so that it runs on neuron core. Since we have separate engines for tensor computation, vector computation, and so on, so we need to do a pre-compilation, which automatically happens when you run the job on SageMaker. It does the compilation first, and then it runs the training post the compilation. And once the training is done, all the model artifact is copied to S3. So with that, I will pass it on to my colleague Raghu, who is going to run us through on inferencing using SageMaker and neuron-based inferentia.
Thanks, Arun. This is great introduction on SageMaker training and how to use how to use Trainium on SageMaker. So in this next section, we look at how you can use the deployment aspect of it. If either you've trained your model on SageMaker or elsewhere, how can SageMaker help you deploy? And we'll also look at some aspects of cost saving and performance saving here. And then my colleague will follow up with a session on Inferentia itself. So looking at this, So we'll look at the section for deployment. In SageMaker, Amazon SageMaker is a managed service that accelerates every stage of machine learning lifecycle, right? We discussed, right? So certain aspects of it can whatever you do on your training can be different from what you do on inference. So SageMaker helps you provide an end user experience such as Jupyter notebooks, a low code no code solution through SageMaker Jumpstart, and tools and libraries for you to easily deploy these models on SageMaker. And also to top it off, you have capabilities to monitor these models by using SageMaker Model Monitor, and it all integrates well into your SageMaker pipelines, where you can tie all things together, have a logic where you can train and deploy your models, monitor your models, and then entire life cycle of management of these services. Like other AWS services, we also have an ability to provide a access through APIs and SDKs, as well as consoles and IDEs. So although SageMaker has different components that are natively built with each other, you can use these components independently as well. So like I mentioned before, you can either bring the model that is trained elsewhere or trained on SageMaker. Now specifically, let's talk about the inference capabilities of SageMaker. So if you look at this, SageMaker offers a wide range of inference options. It provides you managed resources and optimize inference performance across your machine learning models. To help you with that, we provide you a way you can deploy it on a CPU instance, GPU instance, also on an inference share too, which we'll concentrate on here. In with an inference share too, it provides you the highest performance of machine learning models. It's a custom design chip with AWS specified for hosting models, and EC2 inferentia to instances based on inferentia chips deliver up to 2.35x throughput and up to 70% of the cost for inference, and comparable to different GPU instances that are available for you. And SageMaker also helps you support by providing multiple deployment options such as real-time inference, serverless inference, asynchronous inference, and also batch inference for your offline workloads. It, in addition to that, it also provides you cost-saving options such as multi-model endpoints, auto scaling options that we'll touch upon in the next slides as well. In addition to that, with SageMaker, you have the flexibility to bring different model servers such as TensorFlow, TouchServe, NVIDIA, Triton, MMS, and so on. And to help you in particular to deploy the large language models or generative AI models, we have launched something called as the large model inference container, which is purpose built containers or deep learning containers that we have to help you deploy these models at scale and get the highest performance at lowest cost. In addition, we also support Hugging Face TGI container, which is text generation index containers as well. So let's take a minute to look at what are different dimensions that you can save costs and also increase your performance on SageMaker hosting. So in this section, we look at the software considerations, what affects your picking of your right instances, and what are the different cost saving options such as asynchronous inference, multi-model endpoints, auto scaling, and also how your savings plan can help you save costs, and also towards the end we'll look at using inferentia to speed up your inference and lower your cost. So let's look at the first aspect of it. So when you look at it, the first thing that we need to do is try to pick the right instance. For that, there are different kinds of considerations you might have to make. So let's start with the software considerations. So let's say your model size is important to understand how much memory that the model will take. So it's important to pick the right instance which has the enough GPU capacity that the model needs. If we're talking about the generative AI models, some of the important considerations could be the output length, input length, the concurrency, the search strategy such as the greedy search or the batch size, etc. Additionally, another 20% of your memory is required for your attention cache or sharding the models across memory, and also your buffer memory. So, and one very useful way of getting a higher performance is by reducing the model size, that is through model compression. What this is basically is reducing the number of layers of connections or reducing the precision of weights and activations by using quantization methods. And we'll focus on quantization, which involves reducing the precision of weights, let's say from FP32 that requires 4 bytes per for using to, let's say, FP16, which only requires 2 bytes. By doing that, you're almost reducing the size of the model by half, and that helps you keep more copies of that model in memory or pack more models into the memory of the same instance. So with in addition, we can use like flash attention, which is a new algorithm that computers extract attention from far few memory accesses. Our goal here is to avoid reading and writing the attention metrics in and out of the memory, and it also reduces the overall inference time. So it basically, think of it this way, as it reduces the memory reads and writes between the GPU for high bandwidth memory or HBM and the GPUs on chip. So in addition, you have different optimization strategies, such as you can optimize with frameworks such as deep speed, faster transform, accelerate to reduce your latency and also increase your throughput, resulting in lower cost per token that your model requires. Some of the questions you will need to ask before choosing the right hardware for your instances. The first and the foremost choice would usually be if the model is compatible with Inferentia 2. If so, it will give you the best or the highest price per performance. You can check the models that are supported on our Inferentia page. If that fits into the bill, that should be your first option. If not, we could look at like something like a G5 instance, which is a single GPU instance, like a G5.2x large. If it that fits in, if your model fits into a single GPU instance like this, that's the next best option. If not, you can look, if you have a bigger model, you can look at like the bigger instances of the G5 family, such as like 12x large or 48x large. Next, you would use a G4 DN instances if your models are smaller in size, and this usually comes with a larger latencies. So if your application is capable of hosting a larger model, this might not be a good fit for you. And finally, if you have a P4D instance, which offers you the lowest latency and accommodates the largest of models, bigger than G5 instances, but these are also one of the most expensive instances that we have. So be sure to maximize the GPU utilization of that instance. Pack more than one model per instance, or more copies of that model per instance to maximize the GPUs here. In addition, most of the transformers are trained with mixed precision, either on FP16, FP32, or BF16. So this cuts down the amount of memory required to train models, and also the memory required to run the inference. So we can cache these models from FP32 to FP16, or even going down to int8, which reduces even the less memory that is required, without substantially taking a performance hit. So these are some of the considerations you would choose when uh, you take into consideration before choosing the right instance. And to help you with that, we have the next capability. So in order for you to help benchmark and load test models in production, and also to speed up your model testing process from a POC to a production state, we have introduced a new capability called SageMaker Inference Recommender. With using the SageMaker Inference Recommender, you'll spend a lot less time, and also it'll provide you the various set of parameters that are required to and the container configurations and environment variables, suggestions of that, so that you can arrive at the best instance, and also the configuration that will work best for your workload. In fact, most of our customers have used inference recommended to right size their endpoint and saved up to 30% of improvement in price per performance. Next cost saving method is something called as SageMaker asynchronous inference. This is typically useful when you have when you have workloads which are intermittent in nature. Let's say you have a large video stream or textual data like an NLP problem that there, but you don't have a stream that's coming in all the time. So you don't want to have an endpoint that's always up and running. So this is where SageMaker and async inference can recommend. Async inference can be very useful. When you don't have this traffic coming in, you would scale down the instance to zero and then only scale up when it's required. So it's a cost saving aspect as well, and it works very similar to your offline inference where you can put in your inputs into an S3 bucket. We'll read from that S3 bucket, and then we have a managed queue here, which basically queues the amount of requests that you can send, all the number of requests that you get onto the endpoint, and then you can control how much of the requests you can. You can also decide how many instances that you want behind the endpoint, and appropriately choose how many requests you want to pull out of the queue. So this is a very useful mechanism when you have intermittent traffic and when you want to save costs. Additionally, as part of your real-time inference, which is your always-on endpoints, like I mentioned, and useful capability is called SageMaker multi-model endpoints. With SageMaker multi-model endpoints, it provides a scalable and cost-effective way of deploying large number of machine learning models, up to thousands of them. It gives you an ability to behind the same endpoint. It provides you an ability to deploy these models behind a same endpoint, and this will be particularly useful when you have smaller models and which are of very similar frameworks. And you can potentially save and you can potentially save up to 90% of your costs by using multi-model endpoints. This is by design. Whenever you have a model that's loaded on a set of models behind that endpoint, we will dynamically load that model and unload that models behind that endpoint as and when you make invocations, and we'll be sure to keep the models in memory which are being accessed more often, so that you don't have any cold start times there. Finally, what we have is using this using SageMaker, using order scaling policies. With order scaling policies, you can dynamically adjust the number of instances provisioned behind the endpoint as your workload changes. There are multiple target tracking policies, scheduled scaling policies, multiple on-demand policies. So basically, whenever your workload increases, auto scaling will bring in more instances and make sure you have more availability. And also, whenever your workload decreases, like if you're using an async endpoint per se, you can scale down the instances to zero, or if you're using a real-time inference, you can scale down the instance to one and remove the unnecessary instances and don't pay for the over provision instances that you aren't using. So this is a very good cost saving aspect of it that most of our customers leverage and gain benefit in. Finally, we have the SageMaker savings plan. SageMaker savings plan is a flexible pricing model for SageMaker, which in exchange of for a commitment of consistent usage of amount measured in dollar per hour for 1 or 3 year term. SageMaker plans provides the most flexible way to help you reduce cost by almost 64%. This does it by automatically using the eligible instances such as notebook instances, on-demand instances, SageMaker processing, inference, and real-time batch instances, regardless of the family or the size or the region of that instance. That kind of brings it to the end. I want to hand it off. We'll start again. With that, I want to hand off. Now that you've looked at different cost saving options with SageMaker, let's look at one aspect of it where we'll look at how SageMaker inference chips help you gain more performance and lower cost for inference. With that, I want to hand off to Casey.
All right, thank you, Rabu. I'm going to start talking about Inf2 or inferential 2 instances and how you should be able to leverage different size of instances for different purposes. And as it's stated here, we designed Inf2 instance, or rather inferential 2 chips as a second generation coming off the inferential 1, which is the first generation custom silicon chip built by AWS exclusively to run inferencing workload in AWS cloud. And ever since then, we see the need to evolve in terms of a custom silicon design, in terms of the kind of a model that we can serve the customer, because as we know, the models are getting larger and larger, and the internal structures are getting more and more complicated. So with that in mind, we design and we custom design and build Inf2 instances, as well as the chip behind it that's powering it, known as inferential 2. So for the Inf2, comparing to the Inf1, the first generation of the AWS inferential chip, we see up to 4 times of higher throughput and also 10 times lower latencies when you run the same model comparing the two. So, and also there is also a bump in the accelerator memory bandwidth as well. And this becomes really important when you talk about how do you run inference job for large language model, for example, or for generative AI models, such as a stable diffusion that translates text into image, for example. These models are complicated and demanding in terms of memory bandwidth in their own rights. So let's look at the 4 different tiers of instance sizes that we offer. Okay. For the first 2 tier in the instance size, you will notice that there is one inferential 2 chip. And one inferential 2 chip consists of 2 neuron cores. So you can think of it as 2 GPUs inside of one inferential 2 chips. And then followed by the next 2 tier. And you have either 6 or up to 12 inferential chips. And so that will give you up to 24 neuron cores, or equivalent of 24 GPUs running separate workers. And as you can see, that for the first 2 tier, these are single chip instances, so that there's no need to connect the chip to chip with a neuron link. However, as you go up to the larger instance size, the workload becomes important enough that, especially for large language models, that you have to shard the model across multiple chips, multiple inferential 2 chips. Then how do you make sure that they communicate? How do you make sure one part of the model flows to the next? Well, that lies in the way how the neuron links works. So that becomes very important when you talk about inferencing a large language model and produce the output in a timely manner. So for that, we designed a neuron link, which is a direct communication between instances and minimize data movement and bypass the data going through CPU. So that also reduces a lot in terms of the latency between the data movement. And as you can see, with the instance size increase, we also increase in terms of corresponding CPU, as well as the instance networking speed. So this is all very important for large language model inferencing in terms of the speed, in terms of the throughput. Now I'm going to talk about AWS Inferential 2's chip and its internal cores. And on this diagram, as you can see, it's actually very, very similar to Trainium. In fact, that is exactly what I want to touch upon. AWS Inferential 2 and Trainium actually shares over 90% of similarity in terms of at the silicon level. And again, what you're seeing is that you see that within the inferential 2 chip, there are 2 neuron cores. Again, think of each neuron core as a separate GPU. And within that particular neuron core, this is where things starts to be a little bit interesting. You notice that we separated out into 3 different engines. There's a tensor engine, there's a vector engine, and there's scalar engine. And this is exactly like how previously Arun explained. That tensor engine handles large matrix multiplication job, vector engine handles aggregation, and the scalar engine handles operations such as activation function. And then in addition to that, there's also a collective communication engine that you see on the top right. And this is actually built to handle fuse ops as well as a gradient accumulation and gradient compression during the large language model inferencing, and to reduce the data movement between the neuron core as well as from the neuron core to the CPU. And the result of it is that fuse ops for data movement can be run in parallel. At the same time, the compute engine is doing its job. The tensor engine is doing the matrix multiplication, and the scalar engine is doing the activation, and so forth. So we parallelize as much as we can from an operation standpoint. And also, noticeably, we also have the neuron link V2, which, like I mentioned, is responsible for direct data movement between neuron device, between inferential to chip to the next inferential to chip. And this becomes very important when it comes to large language model inferencing, because the model is so large that you have to shard the model and spread it across multiple inferential chips. Even during one inferencing round, you need to kind of collaborate, if you will, between the chips in terms of how data is being moved from one level of the model to the next. And this becomes important that only if you have a fast speed linkage between the chip that can this be done. So that's what Neuron Link V2 is good for. And in addition, we also have the network connectivity up to 100 gigabit per second in the largest instance in 2.48x large. And also the high bandwidth memory is used to hold and cache, if you will, as much model weights as you can, so that the model weights doesn't have to be recalled and load and unload during the inferencing step. So all these things add up to reducing latency and also increasing the throughput. AWS Neuron SDK makes it easier for developer with AWS Trainium and AWS Inferential Access. So with the powerful hardware that's custom built and purposely built for large language model inferencing job, in order for user to access it, we need to also have a software stacks that can make these hardware features accessible. And to that end, we make sure that our framework support is consistent with what's most popular and most advanced in the industry, in the community. So for example, we see PyTorch and TensorFlow as the main framework that we provide support, ongoing support and evolution of Neuron SDK in order to fit into the PyTorch ecosystem as well as TensorFlow ecosystem. And also we have strategic partnership with Hugging Face, who is probably the most famous and one of the largest open source model repo in the industry. And also, we are also part of the OpenXLA consortium for even larger and more complicated model build out in the future. Now, for Neuron package itself, we provide compiler, runtime, and the developer, as well as a monitoring tool such as Neuron Top for user to take a look, as well as to leverage the hardware features that the inferential tool supports. And on the bottom, and you see that these are the links to our official documentation for Neuron, as well as a GitHub repo for a lot of example and code base for you to try it out. So long story short, AWS Neuron is an SDK built exclusively for you to leverage and access hardware that we design, such as Trainium and Inferentia. Now I'm going to talk about popular model support for TRN1 and INF2. And this is as of the latest update that we have. And at the recording time, currently, as you can see, we're up at a Neuron 2.13 release. And on these two tables on the left is about language model, and table on the right is about computer vision model. So as you can imagine, in the generative AI field, invariably it comes down to these two domains, generating language or generating image or video in the future, right? So you will notice that in both cases, we support inferencing more than we do support training. And that is because that a lot of our customers want to start with a model that they already have access to. They're happy with their model and they are ready to deploy it in production. So, or that they train their model elsewhere from some other domain or from some other infrastructure. And they have the model weights, they have the model file, and now they want to put it in production. So naturally, we look at the customer priority, and it turns out that inference is a much higher demand, much urgent demand from the customer perspective, because this tells them that AWS is ready to support the model that they build in-house or the open source model that they grabbed from the ecosystem, and they are ready to deploy it, and now they're looking for a cost-effective solution, and AWS offers it. So that's why we focus on inferencing first. And as you can see on the left, from the language model perspective, a year ago, we started off and making sure that we support BERT, as well as different flavors of BERT. And today we're very, very solid, and we support almost all the BERT models there is available in the industry. And this year, we started to work on decoder-based models, such as the GPT type of the model. And again, you see that our coverage is starting to emerge in that GPT model families. We start up with inferencing, and then you're going to start to see more and more coming soon. For example, like GPT-J, like Bloom for training, for model training support. And just very recently, we announced the support for Llama-based model for both inferencing as well as support. And also for the encoder-based model, encoder-decoder model, such as T5, we have training support as well, and inferencing support is coming soon. And for computer vision models, such as diffusion, stable diffusion model, currently we support 3 different types of a stable diffusion model for inferencing. And then also something smaller, vision transformers. Yes, we have a very good coverage for both training and inferencing as well. Next slide is INF2 benchmark for large language model inferencing. And from here, you can see that our INF2 instance actually provides a very good throughput, for example, for some of these large language models that's currently in trend. And starting with the Amazon's own Titan model to some of the public foundation model, and then also the third-party models. Next slide is about the benchmark result that we see through SageMaker and AWS Inferentia 2. And in here, we put together a side-by-side comparison of the token per second, or rather throughput, if you will, of a GPT-4J model. And as you can see, in a comparison with the competitive GPU instances, our throughput is actually much higher. And likewise with latency, when it comes to generating image for the computer vision model, such as Stable Diffusion. We provide exactly the same latency in terms of image generation when it compares to a competitive GPU instance, but at the fraction of cost. Now I'm going to talk about something very unique and specific to the runtime architecture that's known as how do you actually support large language model in inferencing, and how do you make it work within the SageMaker ecosystem. And as it turned out, we make sure that our Transformers Neuron X package, which is a inferencing package that Annapurna team built to support large language model inferencing, we make sure that it's compatible with the SageMaker architecture, and in such a way that it is wrapped around in the DJL serving, and from the DJL serving, it's exposed through SageMaker user interface. But let's take a look at the inner working of what does it take to actually serve a large language model. It turns out that large language models such as GPT level kind of a model is so big that you cannot just shard it along layer by layer and then split it across neuron core or neuron devices. You have to split horizontally, meaning that within one layer, you have to split the tensor weights, if you will, across it in such a way that the tensor weights are distributed itself. As a tensor, it's split among all different neuron cores. So that's what Transformer Neuron X does. And that's what the parameters such as tensor parallel actually means. It means that this is how I'm gonna split the model weights. Basically, not from layer to layer, but rather cross a layer and horizontally through the tensor. And the way to do it is using the Transformers Neuron X package. That, as you can see, that if the tensor parallel degree is 4, that means that I'm going to shard the model from forward pass all the way to the output horizontally in 4 parts. And Transformer Neuron X will be responsible for collecting the model weights, forward propagation, aggregated together, and produce the output. And now you can see the importance of the neuron link V2. And without neuron link V2, this wouldn't be possible, because you have to link together the forward propagation result of one part of the tensor to the next in a speedy manner. Otherwise, the user experience is not going to be ideal, because it would take you forever to wait for the next worker to propagate likewise the forward pass of one portion of the tensor all the way through. And this is why we designed the neuron link V2 for exactly this purpose. And now, reaching towards the end of the presentation, I'd like to point out these 2 useful websites, one of which is a result of our collaboration with Hugging Face Optimum team. And the Hugging Face team built out an Optimum Neuron API to really enable Hugging Face model users to use one common or unified API style to run training and to run inferencing job. And on the bottom, there's a link to AWS Neuron Link for the documentation. And in there, they contain a lot of examples, as well as introductory materials to a lot of things that we talked about today. For example, tensor parallelism. Why do you need it? And for large language models, how do you use it? That as a knowledge to select the instance size for your inferencing job. So with that regard, today, I think what we have covered is a distributed training with AWS Trainium. And then we also discussed the neuron highlights, as well as training and inferencing examples shown in the SageMaker. And then also with Trainium and inference instance details and the kind of a benchmark you can expect from us. And next, these are just a few customer studies. So for Finch Computing, which is one of our customers that leverages INF2 and TRN1 for their NLP job load, this is their testimony. So with that, I'm going to end right here. Thank you very much for your attention.